presentation show at the conference Towards Sustainable Aquafeed. It was presented at Victon Asia in Bangkok, September of 2022. My name is Michel Pereira, and I am the Global Application Manager for Aqua Pet business within Andritz. I'm working in this company for more than 7 years now. My focus is mainly sizing equipment, process evaluations, and trainings. I live in Brazil. I am graduating in mechanical engineering with a master in science in mechanical in aeronautical engineering, and I've been working in this field of human food and animal feed for more than 10 years. I would like just to introduce you to the business units of my company. We for sure work with aqua feed and pet food extruded feed, but we also have a divisions working with animal feed, mainly pelletized, biomass, and waste and recycling. And also we have this global presence, which makes we always have a office close to your business to give you good service and attendance when needed. Now let's jump to this presentation, which is called Efficient Use of Energy in the Extrusion Process. I would like to give you some tips and inputs on things that you can improve in your own process in this goal of saving energy and being as efficient as possible. So let's start with the advantages of using an extruder to produce fish feed. Basically, we can improve the nutritional value of most raw materials because while we extruded the feed, we start cooking it, so the digestion in the animal will be easier. We also can produce the feed with the right density. In aquafeed, it makes all the sense because some fish will eat floating fish feed, I mean in the surface. Some fish like slow sinking fish feed. Uh, for example, the salmon, it's a carnivorous fish. It needs to attack the prey. So while the feed is slowly sinking, it attacks the feed. And also we have fast sinking, what we call, which are fish that lives in the bottom of the sea. And for example, also shrimp. Shrimp, they live in the bottom, and the sink needs to quickly goes to the bottom where they can find them. With the extrusion process, we also in controlling the bulk density. In fact, we are controlling the amount of pores inside the feed, and so we can create more or less space, which will change the bulk density. But that also helps in the end to add high oil content. For example, if you are preparing salmon feed and you wanted to introduce a 30% of oil in the vacuum coating step process, it's needed to expand the feed. You cannot compact it in a pelleting machine and later add so much oil. So this is kind of a control that the extrusion process gives to you and helps you to produce the feed according to the desire of your customer. Also, another benefits is that the extruded feed have longer water stability time and also higher mechanical resistance. This is because of the starch content that we add into the formulation. This starch, when activated and cooked by the conditioning and the extrusion process, it will create a strong matrix that will give this higher mechanical resistance, which is connected with the longer water stability. Some disadvantages of this process, for sure, the investment and capital equipment is higher when compared to a pelleting line, and also the operators, they need to be more skilled. It's more training with the product, mainly if you produce different kind of fish in the same line, fish feed in the same line. If you produce a sinking fish feed and floating fish feed, the configuration and the way to conduct the machine is different. So these are the things that your operators must be aware. a general overview of a flow chart. This is the standard Aqua flow chart that we use within Andritz. We can see a section for intake where we are delivering the raw materials, in this case with trucks. We also have a waiting session where we have the storage bins and we have a scale. So we start to prepare the formulation here, 20% of this material, 10 of that, 5 of that. Everything measured here makes the batch. This batch goes to the mixer. This is the ideal version, but sometimes we only use a vertical mixer here. We can see double grinding system. I would assume this will be used for shrimp line, for shrimp fish feed, where we need a very fine grinding. And also after the grinding, we can see this selective sifter, which is removing all the particles that are not grinded fine enough and passing them through a pulverizer. So I could even say that this line was meant for shrimp feed or some starter fish feed, because when we use the selective sifter, we are aiming for very small products. The idea here is to avoid clogging the die plate. If we don't have that and the particle reduction is not properly made, you start up the extruder and in 10 minutes, 15 minutes, you have your clogged die plate, and then you need to stop the line and disable the die plate and clean everything. That will consume your time. So your efficiency will not be as high as possible. Uh, After we took all this care in doing the particle size reduction and passing through the sifter or the pulverizer, so now we know all the particles here are in the right size. Then we do the final mixing. Here's the step where we can put some microdosing, some vitamins, or this material in small amounts, everything mixed, and then we came to the extruding section. So we have a vertical mixer here just to avoid segregation. We can see it has load cells, so we are using weighting loss system to calculate the capacity of the line. Everything is calculated here in the dosing screw or feeder screw. So if 10 tons of a meal are passing here right now, and I'm asking 50% of water, and 10% of steam or whatever, everything is calculated by based on this capacity in the dosing screw. We have two conditioners. In the first one, we're gonna do liquid addictions and steam. So we can add water, we can add oil, we can add lecithin or whatever, and the steam to start the cooking process. The second conditioner usually is used for retention time, no liquid additions on the second one. And then the feed comes to the extruder. In this case, it's extruder with an ECS, so we know they are producing sinking fish feed or salmon, or shrimp, as I said at the beginning. And in this case, the product just falls from the extruder to the dryer using the gravity. The drying process happens, in this case, a 3-layer dryer. And then we came to this another sifter, which is removing fines and clumps, is a 2-deck sifter. So from this sifter, just a good product comes to the coater, because here we're gonna coat with a very expensive oil or palatant or whatever. So we don't want to waste any product with fines that will be removed in this next sifter here, or with clumps. We wanted to only sell good product to our customers. So after we clean, we go to the uh, vacuum coater. We add the flavor, the oil, the pounder, whatever type of aquafit is this, and then later the next step is cooling. So we need to cool the product to avoid any kind of a condensation here in the storage bins or here in the packing machine. So you see, after the cooling, it goes to another sifter. Sometimes the sifter is placed under the storage bins, which I think is a better location. And then finally we can pack the product. So this is an overview of the extrusion aquafeed line flowchart. And now let's talk a little bit about the grinding process. Uh, the idea with the grinding process is to achieve the ideal particle size without grinding too much or without grinding too coarse. What is the idea here? In general, grinding finer is better, but it uses more energy and it can be sometimes more energy than necessary, so we want to avoid that. So the rule of thumb is that we should grind the product at 1/3 of the die plate hole diameter, which means if I'm doing a fish feed with a 4 mm die plate perforation, that's easy because we divide it by 3, we have a 1.2, 1.3 millimeters, the particle size, and that's easy to grind. We can grind this with a single hammer mill using 1.2 millimeter screens, and the particle size will be around 800 micra, 90% of the particles. The problem starts when we are doing microfeed. Let's imagine we are doing now salmon, shrimp feed with perforation and die plate 0.8 millimeters. Then we divide it per 3, and we have something like a 250 millimeters. So then starts the problem because we need to grind very finely. And the idea here, so we can see in this picture, we have a double grinding setup. So we use this first grinder with a screen 3 millimeters, 2.5, do a coarse grinding, and we feed it with the second hammer mill that we use 0.8 millimeter screen perforation. And with this configuration, we can achieve 90% of the particles below 250 microns. Is still necessary the sifter here that will remove the 10% that statistically is above the 205. So then that usually we're gonna rework here or pass through the pulverizer as I showed you before. So this is the idea. We are trying to avoid the clog of the die plate, but also we can see that when we grind the material fine enough, we increase the surface area of the particles. So when it goes to the digestive system of the animal, it will be better absorb the nutrients. So this is one positive point. Also mixing, when you have all the product more or less with the same particle sizing, the mixing becomes more homogeneous, which will make the extruder process, the conditioning process and the extrusion process much more smooth and steady. When we have the right particle size, we can start the conditioning process and we can cook the whole particle from outside to inside, everything fully cooked. If you have a too big particle, usually you'll be able to cook only outside. The core of the particle is still raw and hard. And when that particle goes to the extrusion process, the knives or the die plate may cut that particle exposuring the core raw material, the raw core of the particle, and that may create fines. So most of the times we see fines in the dryer. They're not coming from the extruder. They definitely don't come from the dryer. They probably are a result of either the grinding is not good enough, not so fine, or maybe sometimes too much oil into the extruder, so you cannot cook properly, and that's why you have that raw uh, cores into the particle that will generate fines. So again, the idea is to reduce until 1/3 of the die plate perforation. And sometimes what I see in the customers is they will have this double grinding setup here, and they will use the two hammer mills when they are producing product, close to 2 millimeters or smaller. When they are producing in the same line bigger products, they will bypass one of the hammer mills and use only one of the two. And that's enough. As I said, when you're producing a product, let's say 4 millimeters, you don't need to grind so fine. So this, I'm resuming this in this table here. We can see that it's a balance between capacity and quality. For example, if you have your product, you analyze it, and you think it is not good enough, you'd like to have a finer grinding. What you can do, you could adjust the screw perforation. If you have a smaller screw perforation, you will have a finer result. Or you could adjust the tip screen. That's something that we usually don't do because you would need to either change the frequency of the hammer mill or the length of the hammers, the beaters. The airflow, this sometimes I found with customers that they have a too much airflow than what was designed for that specific hammer mill. And when you have a too much airflow, what we can see is that we have a coarse grinder. So everything was was correct. The screw 0.8, the distance, the hammers to the screw, everything, but the airflow was too high. So the result was a coarse. And this you can follow the table and imagine for sure when we are grind finer, the capacity of the same equipment will be smaller than when you grind coarser. But this is the balance that we need to find to be effective in the product you're producing for your market. Now a little bit about the conditioning. As I told you, this is the first conditioner. We can see here we have a manifold for the steam and also not show we have the water injections. So the idea here is that we create this pattern of loading level inside of the conditioner. How we know what is the loading level in my conditioner? The easiest way is when you push the red button, the emergency button of your line, and you shut down the whole line with product inside. Then you go there, open the doors of your conditioner, and you see inside. If it's not so good as this, you can change the pedals angles here, trying to search for that. And then next step is to adjust the steam valves to have a more or less this pattern here. We don't want too much steam in the beginning because this can avoid the flow of material that is coming to the conditioner, and we also don't want too much steam here in the end because this can impact the PT100 here, which is measuring the product temperature. It may start to read the steam temperature, and that's what we don't want. We wanted to measure the product temperature here. Besides that, you see, we respect this rule of a 40 to 45% maximum filling level. Why? Because the idea with the conditioner is to throw the product into the air, more or less what you can see here, where the water represented in this yellow color and the steam in blue, they can have a good mix in here. So we throw the product in the air where the water can be absorbed and also the steam to start to heat up the product. And this make the conditioning process more efficient. If you fill it up too much, then you don't have space over there and the mixing property is not so good. This is a unique design used by Andritz, and I think it's very effective because you have a good mix in between the water, the steam, and the product. One more thing about the conditioning, you need to have enough retention time, and the way you estimate the retention time is a function between the capacity of your line and the volume of the conditioner. So sometimes we're gonna put the two of them, as I explained in the beginning. The first one will receive the liquid and the steam additions, while the second one is for retention time. We're gonna add the volume of both of them and make the calculation to give you the retention time needed. Usually for shrimp, sorry, for fish feed, where starch content is more or less 10%, we need the 2 minutes of retention time. And when we do shrimp, we may use more. We may use the 3 minutes of retention time. So basically, sometimes, most of the times we use the two conditioners, and sometimes we need to use the three of them. Now we move it to the extrusion part. And also here, the way we operate the extruder can be more efficient or less energy-wise. So the extruder can produce small pellets like 0.6 millimeters, sometimes 0.4, 0.5, depending if it's a single or is a twin screw extruder. Usually the twin screw can work better with smaller die plate perforations. The extruder can handle with higher temperature and moisture come from the conditioner and compare with a pelleting machine, which means we can conditionate much better the product before the extruder. And when the product comes to the extruder already with the starch pre-activated, the job on the extruder is easier and it can have a higher capacity. Detail here is that we need to size the die plate, which is installed here inside the die holder with the correct design if we want to produce a sinking or floating product. The die plate has an impact on that. It's very interesting to have a variable frequency drive here in the main motor so we can control the amount of energy we are putting into the main screw. I mean, when you do sinking fish feed or shrimp feed, you must control that energy. If not, you put too much energy into the feed and the feed is going to float, not good for the shrimp. Uh, the oldest and most usual way of controlling the expansion is adding oil, which is expensive. So if the recipe has oil, they will add oil into the extruder, but not all the times. But the most common is to add water into the extruder barrel, something like a 3 to 5%. If you add a really small amount of water, like a 0.5%, or even steam at the extruder barrel, you can slightly adjust the bulk density, making the product a little bit lighter because you are increasing the evaporation and the expansion, so the product becomes lighter. But if you add too much water, from 3 to 5%, that water will work inside of the barrel as a lubricator, and that will decrease expansion. The bad thing about this technique is when you put more water here into the extruder process, you need to dry more water into the dryer process. And that difference will, because the dryer is the most expensive process in the extrusion line, that may have a negative impact. So Andritz has developed a solution for this problem, which is the ECS, the expansion control system. So instead of adding water into the barrel to avoid expansion, what we do is recreate this pressurized chamber in the front of the die plate, as you can see here. It's connected with the compressed air supply of your factory, and it can raise the pressure here up to 2 bar. So basically, in the atmospheric pressure 1 bar, water will boil at 100 degrees. But when you can raise the pressure here to 2 bar, the water will boil at 120 degrees as shown here. So the consequence is less evaporation happens after the die plate, because now the pressure is higher here in the knife housing. And because of that, the product becomes more heavier. So comparing when we add the first technique I show you, when we add water into the barrel, the final product after the extruder will have a moisture content of 21%, 30%. So then you need to dry that into the dryer until 10%. That's the usual. Your range of drying is 20%. When you use the ECS, you don't need to add that water into the barrel to control the expansion. So this product now will be moisture content 25% maximum. And then you need to dry 25 up to 10. So now you have a 15. This is the difference. From 20 to 15, it's 25%. So when you add water into the extruder barrel, you use 25% more energy into the dryer. So this is a very competitive technique for your process. Use pressurized air, compressed air, which is cheaper to obtain than to evaporate water into the dryer. Also, we have developed what we call the microfeed system, which was meant to boost the capacity of the extruder when producing really small products, what we call the microfeed. For example, if you're producing, I just have a Dix extruder for shrimp feed. When it produces 1.8 millimeter product, the motor usage is almost at its maximum, and the capacity of the extruder is limited by the main motor. When we started to produce a smaller feed in that same extruder, let's say now I'm producing shrimp feed with a zero 0.8. Now the situation is the perforation is so small to have a more or less the same total open area in the die plate. I need to put the holes much closer to each other. And then comes a resistance problem. If they are too close, I may break the die plate with the pressure inside the barrel. So that's why it was developed a bigger, you see here, we changed the die plate holder, and also the die plate's much bigger now, it's 40% bigger. So what I can do here is I can put that really small perforation, 0.8, the amount I need to have the same open area as I had before with 1.8 millimeters. And then I can basically put 40% more perforations of that micro, and then I can boost the capacity when I am producing micro pellets. It will not change the capacity when I'm producing 1.8 because the motor was already at 90%, 95%. I have no more power to put in the shaft. But when I was doing 0.8, the motor was being used at 60% or something like that. Now that I have a bigger die plate, I can use that motor 8 or 90%, and that will increase the capacity. We have a good results changing from 20 to 40% the increase in capacity, mainly with the microfeed 0.8 and 1.2. Now discussing a little bit about dryer. As I said before, the dryer is the equipment that has the highest energy consumption in extrusion line. So I just developed this basic drying curve to explain you how it works in the dryer process. If you send me a sample of your product and I put in a small dryer I have in my laboratory, for the first minutes and start the drying process, you see there is no drying because the sample was cool, and this is called the warming up period. So I'm just warming up the sample. When it starts the evaporation, it starts in the constant rate. You can see it's almost a straight line here. And this is the period in the beginning of your dryer, first and second drying zones, where we have the highest evaporation. So this is what we call the convection, you see. So this phase of the drying process is limited by the surface evaporation. So I needed the highest energy and airflow I can put until I came to the critical content. Critical content is where all that surface water around the pellet now is gone, and we need to wait for the water from inside the particle to migrate to the surface to be evaporated. So that is what we call the decrease rate. And here the speed of evaporation is not ruled by the temperature or the airflow, but by the retention time, because now it's diffusion. We need to give time for that water to slowly move from inside the particle to outside. What I'm showing here with this curve that I made this experiment at 100 degrees is that if I started with 100 degrees and finish with 100 degrees, in the end, my product temperature will first cool down and then raise up again. So the idea here is that we can work in a dryer using decreasing temperatures. Let's say I start with 120, 110, and here after the critical content, I should use much lower temperature, something like 80 to 90 degrees. Can I still use the highest temperature I was using before? Yes, you can. But then you are wasting energy because you are started to heat up the product. This is a dryer, not a heater. And some products are more sensible to the temperature, so you may start to have a losing of vitamins and this kind of nutrients found in the feed. So the idea when you do these decreasing temperatures, once you have what we call here the evaporative cooling, you keep the temperature down and the product will leave your dryer at a temperature of 60 or 70 degrees. Also very important for a drying process is the homogeneity of drying, which means if I take a sample here, another in the middle, and another over there, I want all the samples to be more or less in the same range. We can achieve in our dryer a maximum dispersion of 0.5% because we can do a very even bed loading. We use this motor servo dryer, which is controlled by computer. If you have a mechanical distributor, it always has the same speed in all the points of the trajectory. So there will be a tendency of more product on the sides, and here the humidity will be higher if you take a sample. When you have a vertical dryer, it usually has this rotary feeder in a squared box. So you can imagine the feeling will be something like that. If you take a sample here, will be driest than a sample over there. Also, what we do in our dryer, we have a placed this humidity sensor here in the exhaust tube. So we are controlling the humidity level of the air here because we don't want one, the air to be too dry, so you are wasting energy. Two, the air to be too wet, so you have a condensation problem that may lead to corrosion and everything. So the drying process, the idea is to have this balance. And for sure, you can imagine in two different seasons, from summer to winter time, you need a different adjust in the dryer. So we have all this implemented in the control panel to help the operation by the operators. So finalizing my presentation, I just like to remember some key points. We're gonna do the grinding process only as good as necessary for that specific feed. Don't over grind, it's gonna be a waste of energy. The deconditioning process is very important to start the activation of the starch, which will help to increase the capacity on the extruder. In the extruder, the idea is to have this precise control of the expansion, and I gave you the suggestion to use an ECS. And then for sure, the drying is where it uses the most of energy in the extrusion process. So you must have the correct parameters for the drying, avoiding any corrosion problems, and also avoiding to waste energy using too dry air. I would like to thank you very much for watching this presentation to the end, and I really hope it was useful for you. And I also hope to see you in the next Aquafeed event. Bye.